Okay, as we derive our equations for control volumes, we're going to introduce a number of items of notation that we're going to have to use. And so I'm going to spend a few minutes just giving some definitions of things that we'll use. And the reading that goes along with this is a lovely detailed handout that was prepared by my late colleague Ein Sonen at MIT that's called Fundamental Laws of Motion. And we're going to think about how to apply those to a number of different things, particularly the idea of a material volume, and we'll generically indicate that by the acronym MV. And this might be time dependent, and so we'll use MV as a function of t. And we're also going to use this idea of a control volume, and so we might call that CV as a function of time. And we're going to spend some time defining what these things are. So in general, what we want to do is we want to apply conservation equations to a material. So I've indicated the material here in yellow. And so we might be interested in the idea that there's a volume of material. So our material volume, as we might write here, is everything that's in yellow right here. And it's in a bounding box or in a volume that we'll call our control volume, which I've indicated in pink right here. And so this is our control volume. And we want to understand the idea that if this is what things look like at time t, then as we advance the clock to some time t plus dt, then things may change. And in particular, we're interested in this idea that these things may move in different directions. So our control volume may deform. So this would be, if this was our control volume, which would say is the shape of our control volume at time t, then at the next instant in time, our control volume at time t plus dt may have deformed like this. And in general, our fluid, which is, I've indicated here in yellow, may be moving through this region. So it may be moving through this with a velocity v of x and time. So at the next instant in time, the two do not any longer intersect. And so our material may have moved out in some regions or in some regions. And we have to take into account the idea of these extra regions that are created or destroyed. And that's what we're going to have to spend time thinking about very carefully. If you want a really good physical example of this, you might think of an example of, let's say, a balloon, where I might fill my balloon with, say, a radioactive or a poisonous gas. And at time t, all of the gas is in the balloon. So this is what things look like at time t. But at time t plus dt, if I open this and I let go of the balloon, then I might be interested in where the balloon goes. I might be even more interested in thinking about where the poisonous gas has gone. And so we have to recognize that the balloon may be going in one direction and moving around the room, and the gas is moving in a different direction. And so we have to be able to describe both of those. And so this leads to an important idea of the distinction between the material and the material volume, which in our case the material is our poisonous gas, and then the control volume, which may be the balloon. So in this case our balloon is the control volume. And in each case, they're defined by both the volume and the surface that bounds them. And so we may choose to use a dotted line to represent the surface. And so we are going to introduce the idea of bounding each of these regions by a surface. And we're going to think about what happens to both the balloon, which may everywhere have a velocity, and the fluid, which has its own velocity. So to distinguish between these, we've already written that the velocity for our material, we'll write v, and so we'll think about the velocity of our object. We'll write it with a subscript c to indicate that it's the velocity of our control volume. So our velocity of our control volume may be moving everywhere here, vc. And that may be different than the velocity of our fluid, and so we might well expect that we're going to see that relative velocities play a role as we go forward. And so there's lots of notation for us to think about, but I want to connect this back to things that you've probably seen in your undergraduate classes or in earlier classes. So one way of specializing things is to recognize that we might take the particular case when the velocity of our control volume is equal to the velocity of the fluid. And so in that case, the two do not move apart, and the two stay together for all time. And so then this leads to, we would see that in the case that we did this here, let's say that there was a deformation, then if our control volume deforms like that, and our velocity of our fluid is everywhere the same, then at the next instant in time, the two still overlap. And so when we have a particular case like this, it's always the same material. So this, we can say that this is always the same material. And so in the past, you've probably called this a closed system because we're essentially dealing with constant mass. Finally, we may shrink this to a point. So we may shrink this to a point. So instead of having our finite volume that we could call the control volume or the material volume, we might shrink it to a point. And then we would just have a small differential piece of material, which we might say has mass rho del V. And then this has a velocity, and the velocity is the velocity of the fluid, which is the velocity of the control volume. It's just point mechanics. And that's essentially where we already know how to apply conservation equations. We know how to conserve mass and momentum and energy for a material point. And so by going up to an integral scale, we're just going to change and we'll have an integral for a quantity. However, we also need to think about systems that look like this, and you've probably also seen systems like this as an undergraduate. And so the first simplification that we might say is we might consider cases where VC is equal to 0. And of course, that's what we would call a stationary control volume, which of course makes life much easier. So we might then think about a control volume where maybe our control volume is a box. Looks like this, that's not moving anywhere, and fluid is moving into our box and out of our box in different directions. So maybe we're going to have a fluid flow like that. So fluid does enter and exit our box, and so this would be unlike this. Instead of a closed system, this would be an open system. And then we can simplify it even further, where we might say that our box is closed, and instead of there being velocities everywhere, maybe our box only has a few places where fluid can come in and out. So maybe we'll have a couple of different inlets and outlets of different sizes. But now this should be something that looks very similar to things that you've seen in the past, where we may have fluid coming in, and we might call this V1. There might be fluid going out at a point V2, and fluid going out at another point V3. And it becomes very clear that this is similar to things that you've probably thought about before, where we might draw a control surface around our object. And we might just think about everything that's going on inside there, including the fact that the fluid may be bringing in a quantity, there may be heat being transferred into the system, there may be shaft work being taken out of the system. But all of these are kind of problems that you've probably seen in the past, and to make life easy, you typically assume things like you might assume uniform properties. Across inlets and outlets. And so in heat transfer and thermodynamics, you've probably seen systems like that. And what we want to be doing is developing a general way of describing all of these things. And so we have to think about what is the quantity that's being transferred across these ideas. And so this comes back to the idea that the quantity may be some generic quantity F, which is written in terms of the amount per unit volume integrated over the volume. And we can also write that in terms of the integral between the amount of per unit mass, which is an intensive quantity F, multiplied by the mass per unit volume, integrated over the volume. And so we can think about any quantity that's carried around by the fluid, and we want to be able to describe all of these ways together. And so the way that we're going to do that is through the idea of the Reynolds transport theorem that we're going to derive on the next page. And it allows us to convert between these ideas. The key idea that's behind the derivation is the idea that at the particular time t, where we're going to do this, then at the time t, as we've shown here, at this point the material volume is equal to the control volume, and the material surface that bounds it is equal to the control surface at time t. And with that recognition, that will allow us to convert between a volume description based on control volumes and a material volume, which is really based on the idea of a fixed amount of mass. And so on, in the next lecture, we'll see how to write down that idea of what's called the Reynolds transport theorem.